Jai Hind students, I'm back with my YouTube channel, and today in this particular session we'll be discussing the factors on which the value of acceleration due to gravity depends. Now in the previous session what we have discussed was the value of acceleration due to gravity on the Earth's surface, that was obtained to be 9.8 meter per second square. Then we have also determined the value of acceleration due to gravity on the lunar or moon's surface. That was found to be 1.63 meter per second square, isn't it? Now in this session we will discuss that the value of acceleration due to gravity varies from place to place. It depends on various factors. It depends on height, that is the altitude. It depends on the depth. It also depends upon the shape of the Earth. It is found that the value of small g at poles is different from the value of small g at equator. 9.8 meter per second square, that is just an average approximate value of small g. But it varies, it can vary. At some place it can be 9.79, at some other place it can be 9.78. At some still other place it can be 9.81, 9.82. So 9.8 may be considered to be the average value, right, on the Earth's surface. Now students, it also depends upon, besides these three factors, it also depends upon the rotation of the Earth about its own axis. That we'll discuss sometime later. It's a higher concept. So here, before we start discussing the factors on which the value of small g depends, we need to find out an expression for acceleration due to gravity in terms of the density of the Earth, right? So let's first find it and then we'll fall back to this particular topic. So students, as I stated, Earth, for all practical considerations, it can be considered to be a sphere of radius r, right? Its mass is m. Suppose the density of the Earth is rho. Rho is the density. Rho is the density of the Earth. Although in the junior classes you must have studied, there are three different layers of Earth. One is the core having maximum density, the central one. Then the middle section, that is known as the mantle. Its density of the mantle is in between that of core and crust. Crust is the outer layer of the Earth's surface, which is having least density. So strictly speaking, density of various different parts on the Earth is different. But here again, rho is considered to be the average value of the density of the Earth, right? M is the mass of the Earth, R is the radius. And what more approximation we have assumed? We have assumed the Earth to be a perfect sphere of radius r, right? So at any point on the Earth's surface, the value of small g is found to be gm divided by r square. This is the expression which we have obtained for the value of acceleration due to gravity at any point on the Earth's surface. R is the radius. Now what we do is, we will convert this mass into density. Now we all are aware of this formula, students. Mass is always given by the product of volume and density. Mass of a body is given by the product of its volume and density. So mass of the Earth in terms of density may be written as volume of a sphere. You should be aware of this formula. It's 4 by 3 pi r cube. The volume of a sphere of radius r is 4 by 3 pi r cube, and density we have considered it to be rho. It's the average density. So you can substitute this value of m over here. So what do you get? 4 by 3 pi r cube rho, right? So r square r cube. So only single r will be left. So what do you get is 4 by 3 pi r rho g. This is the expression for the acceleration due to gravity in terms of the density of the Earth. Clear, students? This is the universal gravitational constant. This is the radius of the Earth, pi 3.14 or 22 by 7. So This is the expression for the acceleration due to gravity in terms of density of the Earth. Why I have derived this formula is because we will be making use of this expression while discussing the factors on which the value of small g depends. Right? So there is a purpose for deriving this expression. Okay, students. So now let's discuss the factors on which the value of acceleration due to gravity depends. First is the effect of height. So let's start with the first topic, effect of height. After doing this article, we will conclude how the value of acceleration due to gravity varies with altitude, right? So first factor, it is the effect of height or effect of altitude or height. Okay, again let's consider this to be the Earth. This is the center, radius r. Mass of the Earth is small m, this is the center. This is any point on the Earth's surface. At a point on the Earth's surface, that is, A is the point considered to be on the Earth's surface. What is the value of small g? It's g capital M divided by r square. R is the distance between the observation point and the center of the Earth, right? So put this as equation number 1. Now consider this to be point B, which is at a height h above the Earth's surface. Point B is at a height h above the Earth's surface. So distance is to be taken from the center of the Earth. So what is the distance of point B from the center of the Earth? It will be r plus h. Isn't it? It will be r plus h. So at a point B, which is at a height h above the Earth's surface, above the Earth's surface. Here the value of acceleration due to gravity, it will be given by g capital M, universal gravitational constant, that will remain constant everywhere. Mass of the Earth, that won't change, divided by r square. Earlier this was the distance at point A. Now at point B, this is the effective distance from the center of the Earth and the observation point, right? So the effective distance is r plus h. So in place of r, we will replace r with r plus h. Clear, students? Now what to do is second divided by first. What do we get? GB divided by GA. It will be equal to r square divided by r plus h whole square. GM will get cancelled out. So students, over here, constant over here, obviously the denominator is greater than the numerator. Numerator is r square, denominator is r plus h whole square. So obviously it will be less than 1. That is, GB divided by GA is less than 1, or GB is less than GA. A is a point on the Earth's surface, B is a point at a height h above the Earth's surface. So students, what we conclude? With the increase in the altitude, the value of acceleration due to gravity decreases. Clear? From this expression it is pretty clear. G is constant, M is constant, R is constant. So with the increase in the value of h, with the increase in the altitude, the value of small g will decrease. With the increase in the denominator, this value of small g will decrease. So what's the ultimate conclusion then? The value of acceleration due to gravity decreases with the increase in the height or with the increase in the altitude. So at a point on the Earth's surface, the value of acceleration due to gravity will be maximum, and with the increase in the altitude, it will keep on decreasing. So this was the first factor on which the value of acceleration due to gravity depends, right? I hope you have understood this concept. It's make use of this particular expression, gm by r square, right? So by using this expression, you can easily mathematically verify this particular fact. Okay. Now second is, we'll discuss the effect on the value of small g due to depth. So, second point, effect of depth. This is a point on the Earth's surface, right? This is the center, and obviously this is radius r. At any point on the Earth's surface, the value of acceleration due to gravity can be considered to be small g, and it is gm by r square. And students, remember, in terms of density of the Earth, the value of acceleration due to gravity can be written as 4 by 3 pi r rho g. Just now we have discussed this, isn't it? In terms of density of the Earth, the value of acceleration due to gravity is written as 4 by 3 pi r rho g. Rho is the average density of the Earth, g is the universal gravitation constant, r is the radius of the Earth, right? Now hypothetically, suppose this is a point B which is at a depth x below the Earth's surface. We are discussing the effect on the value of small g with depth. So point B in the first article, it was above the Earth's surface. Now this arbitrary point P is below the Earth's surface. Let us consider this point B to be at a depth x below the Earth's surface, right? So this will be the portion width. So this would become r minus x. So we need to find out the value of acceleration to gravity at this particular point, at point B. So acceleration to gravity at point B, that is at a depth x below the Earth's surface. What we get is, we'll make use of this expression, right? 4 by 3 pi in place of r. Earlier it was r when the observation point was on the Earth's surface. Now point B is at a depth x below the Earth's surface. So from the center it is r minus x. Rho, which is considered to be the average density of the Earth, which is constant. G is the universal gravitational constant. Again, it's a constant. Clear, students? So that is why I made use of this particular formula, right? So now what to do is, in order to compare these two, suppose we divide first from second. What we get is GB divided by GA. It is equal to 4 by 3 pi r rho g. It is common, so in the left with r minus x divided by r. So GB divided by GA. Now look, in numerator it is r minus x, denominator it is r. So here numerator is less than denominator. So again this fraction is less than 1. So it is less than 1, which implies that GB is less than GA. So students, again a very very important conclusion, that with the increase in the depth, the value of acceleration due to gravity decreases. So with the increase in the height, the value of acceleration due to gravity decreases. With the increase in the depth, also the value of acceleration due to gravity decreases. So what is the conclusion? The acceleration due to gravity decreases with both increase in the height as well as increase in the depth from the Earth's surface. Clear, students? So where the value of acceleration due to gravity is maximum? Obviously, at a point on the Earth's surface, the value of small g is maximum. Now here I would like to mention a very very important case. It's a special case. Now just now we have discussed, with the increase in the depth, over here, the value of small g will keep on decreasing, Let's consider the center of the Earth, right? At the center of the Earth. This is a very very important case, students. When the observation point is at the center of the Earth, right? So here what will happen is, as the point B is taken towards the center of the earth, the value of x will keep on increasing, and exactly at the center of the earth, this x will become equal to r. So at the center of the earth, x would be equal to capital R. So here, acceleration due to gravity at the center of the earth would be given by, just make use of this formula, this one. In place of B, write G central divided by GA. It will be equal to R minus, in place of x, you can write as R divided by R. So it will be equal to 0, which implies that the value of acceleration due to gravity at the center of the earth is 0. You can directly make use of this particular expression as well. As x becomes equal to capital R, the value of g becomes 0. So students, with the increase in the height, the value of small g decreases. With the increase in the depth, the value of small g again decreases, and eventually and ultimately at the center of the earth, the value of acceleration due to gravity becomes 0. So this is a very, very important result which we will be making use of in the later section, right? So we have discussed these two topics, effect of height as well as effect of depth. Now let's discuss the variation in the value of small g with the shape. As I have told you students, for all practical considerations, we consider the earth to be perfectly spherical. But actually, it is not spherical. It is egg-shaped. It is ellipsoidal. So, effect of shape of the earth. So, earth is actually, it's like this. It's ellipsoidal. It's not perfectly spherical. So, this can be considered the center. This is the pole. And this one is the equatorial region. Consider this to be point P, this to be point E. The radius would be different obviously. This is the radius at a point on the pole, and this is the radius for a point on the equator, RE. It is pretty clear that RE is greater than RP. It's pretty clear or pretty evident from the diagram itself. So, practically we consider Earth to be perfect sphere where RP is equal to RE is equal to R. But actually the Earth is egg-shaped like this. It's not perfectly spherical. It's somewhat flat. So, this distance is comparatively smaller as compared to this distance. RP is less than RE. Right? So, at pole, what will be the value of small g? It will be g, capital M is the mass of the earth, divided by distance, that is Rp, its square, that is Rp square, right? At poles we will consider this distance, while at equator we will consider this distance, right? So put this as equation 1. At the equator, look, G equator, it will be G capital M divided by RE square. This is the radius of the equator, right, at this point. So put this as equation number 2. Now dividing these two, what you get is second divided by first. What do you get? G equator divided by G poles. What we get is RP square, isn't it? G equator RP square divided by RE square. Now look, RP is less than RE, so it will be less than 1. Therefore, G equator is less than G poles. So this is again a very, very important result. It can be verified directly from this result as well. When the distance is large, then the value of small g would be less. When the distance is smaller, then the value of small g would be large. Isn't it? It varies as inverse square law. So anyway, coming back to this, what we have proved is at poles, the value of acceleration due to gravity is much greater than the value of acceleration due to gravity at a point on the equator. This is what we have verified. So basically, G pole, it is maximum. G equator, it is minimum. And at any other place, suppose at this place, which neither lies on the pole or at the equator, at any other place, the value of acceleration due to gravity would be greater than that of equator, but less than that at the poles. Right? So this was the important conclusion. So the value of small g does depend on the shape of the earth as well. So students, let me recap all these three. Right? Value of small g, it depends on height, it depends on depth, as well as it depends upon the shape of the earth. At a point on the earth's surface, the value of acceleration due to gravity is maximum. With the increase in the height, the value of small g decreases. With the increase in the depth below the earth's surface, again the value of acceleration due to gravity decreases. At the center of the earth, the value of acceleration due to gravity is 0. And at any point on the surface, the value of small g is maximum. But at a point on the surface also, the value of small g is different. At the poles it is maximum, at the equator it is minimum, while at some other place, the value of acceleration due to gravity will lie between G equator and G poles. It will be greater than G equator and it will be less than G poles. So students, I hope you have understood this concept. So please keep this in mind. Although while solving numericals, we'll consider this small g to be constant. We'll normally take its value to be 9.8 or 10 meter per second square. But actually, its value varies even on the Earth's surface. Right? It can vary from 9.78 to 9.81, 9.82. But we consider its average value to be 9.8 meter per second square. So I hope you have understood the entire topic. So that's it for today's lecture. We'll continue in the next session then. So do take very good care of yourself and thank you, students.